Hello, wonderful people of the internet, and also MIT Class 18S191 on computational thinking. Today, we're actually going to be live coding the seam carving example that was introduced by Grant a few days ago. Now, if you haven't seen that lecture, please feel free to go into the description. It'll be there, and it gives you a good intuitive description for what we're doing today. Also, while down there, feel free to check out the Discord link where you can leave any comments, questions, concerns, ideas, anything like that, and hopefully we'll be able to pick it up during the live stream. Now, unlike last time, we won't be directly monitoring chat on stream. Instead, we have the three other lecturers available, and you should be able to see them on the side over here, Grant, Alan, and Dave, and they're able to say whatever they want, whenever they want, and they should be able to interrupt me. So it might be a bit chaotic, but hopefully it'll turn out okay. I think that's all we have to say for now. So let's go ahead and get started with a very brief discussion of seam carving, what it is, just in case you missed the last lecture and you don't want to look at it right now. So we're going to start with the same image that we had last week. I don't actually know what it's called, The Persistence of Memory by Dali, I think. But let's pretend that we want to squash this image horizontally. We just want to make it smaller in the horizontal dimension. Now, there's a couple of different ways that we could do that. We could crop the image like this, but cropping has a clear problem in that you're probably going to remove important parts of the image. Another thing you could do is scale the image, but now all the important parts of the image become scaled as well. So what could we do? Well, as humans, we can kind of look at this image and we can kind of see what we interpret to be important parts of the image. For me, I think this thing is probably important. I don't know what it is, but it's probably important. The clock over here, probably important. And so if I were to try to rescale this, but keep all of the important parts to remain with the same aspect ratio they had before, what I might naively do is draw a line that misses all of these important bits of the image and just remove that set of pixels. The idea is that we want to create a set of pixels, or find a set of pixels, that are so not important to the image that when they're removed, the user doesn't even notice they're gone. So for example, we could create a line that looks something like this. And again, it's just a set of pixels that can be removed without anyone realizing they're gone. Now, if we were to go at the top, go through all of the elements at the top of our image and look for all possible lines and all possible paths where we try to avoid all important bits of the image, we might get an image that looks like this. Now, I'm showing this right now because it's kind of important to understand intuitively what we're trying to miss here. So if you look at these lines, they all kind of come together, and they're obviously missing kind of the edge here, and then it's also missing the edges over here and the edges over here. Basically what we're doing is we're drawing lines that are avoiding any sharp change between one pixel and the next. So again, if we were to choose a line and remove one, and then choose a new line and remove one, and a new line and remove one, we'll actually start to get an animation that looks something like this, where the image kind of comes together, and you can see that the aspect ratio of all of the important parts remains the same. Now, at some point, you start to notice that there's weird artifacts that appear. And as you keep going further and further in, you'll notice that, for example, the tree branch up there in the upper left-hand corner here probably shouldn't be doing that, and the clock doesn't look right and all this other stuff. But still, the fact that you can rescale, and in fact, this is called content-aware rescaling in Photoshop, in this way, while keeping the content on the inside relatively the same, is pretty cool. So now we have, I guess, the next obvious question. How does a computer, not us, tell what is important in the image? Grant talked about this on Tuesday. The easiest way is by finding those edges that I was talking about before. And one way to do this is with a Sobel filter. In order to find kind of the change between two pixels, we can put the Sobel filter in there, and this will give us a very brief highlight over all the edges. So naively, what I would probably do is draw a line that minimizes the intersection with the white lines in here. And that's kind of the idea behind this particular method. We're just going to try to find a line that minimizes the times it passes through important parts of the image. And it can tell it passes through an important part because it passes through the edge of that important part. So hopefully that's clear. And we're going to go ahead and move on to the next bit. I'm going to move this into the upper left-hand corner so we have an image on screen. And I'm going to explain what you see right here. Let me go ahead and clear this. And let me also open up the file that we'll be working on today. So if you look in the upper left-hand corner, you'll see an image, and this is going to be basically the image that we're going to try to generate. The middle terminal here is going to be the terminal that I'm coding in, and the terminal over here is the typical Julia REPL. Now, because we only have like 25 minutes, and now 20 minutes, because, I was talking about seam carving for a bit, I have a bunch of functions that are already pre-generated. So for example, the brightness function that was introduced by Grant a few lectures ago is here. We have two additional functions, draw seam and write image. These are just different ways for me to imprint a seam on an image and output it easily, and also write a seam out to file relatively quickly. Now, when we're thinking about what to do with seam carving, for me, I tend to think of three important questions. The first question is, what is important in the image? How do we find what is important? The next question is, how do we find that seam of elements that's unimportant? And the third question is, how do we remove that seam from the image? So unfortunately, due to time constraints, I went ahead and solved that third problem here, and I'll discuss it when we get there. And I've also added a seam carving function that basically takes in an image and then also an output resolution and will squash it down. Now, if you are familiar with the notebook, all of the logic from the notebook stays the same, although the terminology may have changed slightly just because I'm trying to speak it or explain it to you as I'm coding. And in that way, I change the terminology to stuff that I would more naturally say. Okay, so I think we can go ahead and get started with the first function, which will be to find the energy. Now, I do have a reference implementation over on the side, just in case I get stuck, but hopefully we should be okay. So, in finding the energy, what first is the energy? Well, the energy is a term which corresponds to essentially this edge image that we see up here. So I'm simply going to say the energy in the x direction, is going to be equal to what is essentially the brightness, the IM filter of the brightness, and I'll explain this in just a second, brightness of the image, and then we're going to have to do this with a kernel, dot sobel here, and we're going to grab the x dimension of that kernel sobel. Now, there's a bunch of different ways that you could do this. In particular, the important bit here is this IM filter. This IM filter is basically replacing the convolve function that Grant showed before. So just keep in mind, it's essentially an image filter. It's applying a filter to an image. Now, I think that'll work. So if I yank and paste this, and I do energy y, I change this to the first dimension, and then I just say that we return the square root dot of energy underscore x squared plus energy comma y squared. I think this should work. So we're going to go over here and we're going to load an image. I'm just going to call the image, and I'm just going to load 0.jpg. It's just what I called the image. Don't ask me why, that's just what I did. If I do im show of the image, we see it up here. Right. So now I'm going to include the file we just created, and we're just going to run energy is going to be equal to find energy of image. Misspelled sobel. Let's fix that real quick. Oop. And let's try it one more time. Include. And now let's do energy, find energy. And now if we do im show of the energy, we see essentially the same image we saw over there to the left. Okay, so now we're going to get into the more complicated bits of the lecture. So we've already found the energy. Now we have to find something that I'm going to call the energy map. Now what the energy map is this image over here that was green in Grant's lecture yesterday, but I just kept everything in grayscale because, I don't know, I like grayscale. This is essentially a map of what direction you need to go in if you are some random pixel. So the idea is if you're trying to draw your seam and you have some random pixel, let's say, I don't know, maybe up here, right? Well, you're trying to avoid a lot of stuff underneath you, right? So if you find yourself on this location in your seam, the way you read this map is that you're going to go hard right to avoid any object that's coming in immediately, right? So you're going to go hard right, hard right, hard right until you hit this black region and then you go down, right? The idea here is that this set of pixels is the minimum possible energy following any path from basically the bottom up in order to get to that point. So this means that if you're, I don't know, just drawing a random path going up, you'll see that you're passing through a lot of very important objects. And because of that, we're collecting a lot of energy as we're going up, where we're passing through a lot of important stuff. And so again, the whiteness is kind of how much important stuff you've gone through. But I think the thing that everyone's eyes are drawn to isn't so much, the color gradient or anything like that. It's actually these little cones of Dunshire or whatever you want to call them that appear in the energy map. So I want to take a second to talk about where those come from before continuing the lecture. So here on the left, we see the energy. Again, this is your edge detection, whatever is important. I just created a set of pixels that are along the lower bit of the image, and I said there's a blank pixel here and here. Now, it doesn't matter what the value is. We can say they're 1 or 0. It doesn't really matter. The point is that as we're generating the energy, the way we'd read this is, for example, if we're at this pixel here, we're trying to find basically what path will lead us here with the minimal possible energy, right? So basically we could come from this pixel, or this pixel. So we're going to ask ourselves which one has the minimum energy. And it's obviously this one over here. So what we're going to say is, as we move further up, how could we possibly, or what is the minimum energy we could have when we get to this point? So if we do this guy here, well, it has to come from any of these red spaces. So over here, it's also going to be red. And again, this was introduced by Grant also, but this is why the cone shape appears, because essentially the paths can only move diagonally upwards or directly upwards. And because of that, it ends up creating these diagonal paths in the energy map. Now, what we're trying to do when we create the energy map is give a specific pixel that this guy, for example, wants to move to. So in this case, we know we want to move down to the lower left. So we're going to say that we want to move down to the lower left instead of central or to the right. And so the way I'm notating that is that -1 is going to be lower left, 0 is going to be going towards the center, and 1 is going to be going towards the lower right pixel. And so that's how I'm going to be notating this in the future. Okay, and like I kind of alluded to here, in order to generate the energy map, literally all we do is set this bottom layer equal to the energy, and then we just go through every single pixel here, and we look at all the paths they could go to, and then we sum the energy up with the minimal path coming up to it. And this will allow us to create this path in here, and also a set of directions, which looks like this kind of gradient image in here. The way you read this is that white will be going to the right, black will be going to the left, and 0 will be going down. So you can see the flow of the seams as they move forward. Okay, so let's get this done because we are, we've got 15 minutes, but it's 15 minutes. So the first thing I'm going to do is I'm going to go ahead and, one second. I'm going to go ahead and define the energy map, which is the thing we're going to output, as zeros of size of the energy. Let me remove that T in there. And then I'm going to say that the energy map of the very last row and there is going to be equal to the energy of that value as well. Then under this, I'm just going to say that our set of next elements, in the notebook, this was called directions, but I actually got kind of confused as to what that meant. So I'm calling it next elements here, which is also probably equally as confusing. But here's what we're going to say. We're going to say the next elements is going to be equal to zeros, and specifically casting it onto an int of size of energy. Okay. So now we're going to say for size, I equals, in this case, we're going to start from the bottom of the image and work up. So we're just going to say size of energy along the first dimension, -1, because we already have that bottom row created, -1 all the way up to 1. And then we're going to say for j equals 1 to size of energy along the second dimension. And we're ending it in there. Now we just have to fill in what we said before. So again, at every individual pixel, we're looking left, center, and right. So we have to find the leftmost element that we're looking at. I'm going to say left is going to be equal to max of 1, j minus 1. Now the reason the max is in there is because we could be hitting the left edge, and we just want to make sure we don't go beyond that left edge. So similarly, right is going to be equal to the minimum of j plus 1, or the maximum that we could have, which is going to be size of energy, and then along the horizontal dimension. Okay, so now we have the idea of left and right, and now we just have to find kind of the local energy, the minimum local energy of the 3 pixels underneath us, and the element of that minimum local energy. So we're going to say local energy, and then the next element is going to be equal to find min of energy map of, and it should be, yeah, it's I plus 1 because we're going 1 down, and remember that y is kind of flipped in this way, and then from left to right. And I think I need an extra parentheses in there. Perfect. Okay, so what this will do is it will return not only the lowest possible value that could be from the lower path, it will also return the element that it's supposed to be on, but this element that it will return will either be 1, 2, or 3. It'll be one of those 3. So we're going to have to modify that in just a second. So we're going to say energy map of ij is going to be equal to, or sorry, I do a plus equals, although I don't have to because we initialize them all to 0, so I don't know why I'm doing that, but I'm just doing it. Plus energy of ij. And then down here, I'm going to say next elements of ij is going to be equal to the next element minus 2. So again, I just want to be able to add the next element, and it should be, so like whatever element we're on, I just want to be able to say the next element in the seam will be whatever we were on plus the next element. So if we do minus 2 here, it shifts it, so it's now going to be negative 1, 0, 1 instead of 1, 2, 3, so you can just add the next element directly to it. Now there's one catch I have to do here. If the very left element is 1, oops, sorry about the typo there. If the very left element is 1, we're going to have to add 1 because there's only 2 elements in an array, and it ends up working out that we have to catch that. So we're going to say next elements of ij is going to be plus equals 1. Okay, so now if we return, unless I failed miserably, which I could have, but if we return this, it should work. So we're going to return energy map and the next elements. All right, so let's hit it against the compiler and see what happens. Include seems to be fine. So now I'm going to say energy map and next elements. It ran. That's a good sign. Now let's im show energy map, and hopefully, there we go. Perfect image. Exactly what I wanted to see. So this is the same energy map you see over there. And again, we can show the next directions, although there's a reason I left this image on the left-hand corner because the next directions isn't particularly intuitive for me. Sorry, next elements.
So James, may I ask, you just wrote a double for loop.
Yes.
Is that a style question? Is that the best way to do it?
Probably not. There's probably a way to broadcast it or something like that.
Or just, can you just combine the 2 for loops?
So you probably could, because the way Julia works, right, is you can actually go through, obviously I'm explaining this to the audience, not you, but you could probably just have one big loop or that goes through all of the elements immediately, and then you could have like a new index for the inner dimension along J. I just think intuitively it's a bit easier to have 2 separate sets of indices, for one along the X dimension, one along the Y dimension.
Yeah, I was just wondering if you could just delete the 4, put in a comma, and delete one of the ends.
Oh, you want to do this? Oh, wait. So you want to do this. So if you do that, and then you do this. Is this what you're saying?
That's what I'm saying.
Yep.
And then delete one of the ends.
Yeah, and also let me.
I find that easy to read, maybe, you know.
Oh yeah, that's fine.
There you
So
go.
let's write that, include that. And then if we run that, it should still be fine. So then we include im show energy map, and we get exactly that.
Except that it's easy to miss on that line that you have 2 different loops, basically.
Yeah.
There's the counter viewpoint.
Okay, regardless, I think we should keep going. We have just a little bit more to do, and luckily the next bit is a lot easier than it seems. Seems was not meant to be a pun there. It's just seems. Whatever, anyway, let's keep going. So the next thing we have to do is actually find the seam. Now, I'm actually going to create another function here, which is similar to the function we have in the notebook. And this is going to be a function I'm going to call find seam at. Okay, and the idea here is we're going to read in the set of next directions, and we're just going to find the seam at some pixel on the top, looking all the way down to the bottom. So I'm going to say we have the next elements, and then we also have whatever element we're going to start on. I'm just calling it element. It's probably a better name, but I'm just going to call it element and end here. Okay, this is actually surprisingly easy because, again, we already pre-generated the list of directions each seam will go at every pixel. So what we have to do here is simply say that the seam is going to be equal to zeros of integer. And again, the int's kind of important because we'll be using this for indices later, of size of next elements, and then along the vertical direction here. So the next thing we can say is that the seam of the first element of 1 is going to be equal to just whatever the element that you're starting on is. And then here's where the next element's idea is really important. So we say for I equal to, importantly, 2, because we're skipping the first element here, length of seam. And we go in here and we end that. We're now going to say seam of I is going to be equal to seam of I minus 1 plus the next element of, again, whatever row we're on, and then whatever element in the seam we were on before. So seam of I minus 1. So this means that we should be able to just add all of the next elements together, or rather add the next element to the seam we had before, and this allows us to find the seam a bit easier. And then at the end here, we're going to return the seam. Okay. So we should be able to run this, right? So I have a function. So let's run seam is going to be equal to find seam at 100. Oh, actually, I think that was a pre-generated function. So now we're going to say find seam. Next element not defined. That should be next elements, plural. So now it should run. Good. So what I did is I generated a seam starting at pixel 100 at the top and then working its way all the way down. And so now we have the seam, and now I'm going to use one of my pre-generated functions, which is draw seam, just to draw that seam onto an image. And I'm going to call it image2 is going to be equal to draw seam image seam. And then we're going to do ImShow of image2. And now we see that seam here and clearly trying to avoid all the important bits. What's nice is looking at it in comparison here. Like I said before, if we start at this pixel in here, it's going to want to take a hard right and then weave its way into this little black area in here. And that's precisely what you see this seam doing in here. So that I think is kind of nice that it's doing what we expect. Okay, so the last function we need to write is one that I naively just called find seam instead of find seam at. It's probably not the best naming convention, but this is just going to return the seam of minimal energy. Now again, because we can read this map over here as the minimal possible energy that we could be at any point in time. So like if we're at this pixel, that's the minimum energy necessary to get to that point. All we have to do is take that top line and find the minimum element in the top line, and then we can just draw the seam corresponding to that. So this should be relatively easy using the functions we had before. We can just say energy map, and then we can also say next elements is going to be equal to find energy map of energy. And then the last thing we need to do is just say we have some sort of minimum value, which we don't care about. So I'm going to call it underscore, and then minimum element number. And this is going to be equal to find min of energy map. And it should be along the first row, and then it should be just everything along the first row. Okay? So now we should just be able to return find seam at, and now we just have to find the seam at the next elements and then the minimum element. Something like that should work, I think. Let's go ahead and include, and let's just see what happens if we do find seam of energy. Hopefully it doesn't break. Doesn't seem to break, seems to give an okay line. So now let's just draw that onto our image again. So image 2 is going to be draw seam onto the previous image and the seam. And now if we plot that, iMShow2. I think that's because I didn't name it something. Yes, I need to call this seam. And I need to put an equal sign. 1 second. There we go, perfect. So now if we do image2 is equal to draw seam, and we say iMShow image2, you'll see that we have a seam that's over here on the right edge. Now, if you remember from the notebook before, this isn't precisely the same seam, but it's relatively close to the one that we found in the notebook. The difference might be that our energy function could be slightly different due to the fact that we're using a different convolve function or something like that. So now what I'm going to do is I'm going to generate that entire video that we had before with our seam carving function. Again, all the seam carving function is doing is 1, finding the energy, 2, finding the seam, and then 3, removing the seam from the image. And then if we go in here, we should just be able to run, if I did this right, seam carving of image, and then some output resolution, which we're just going to say is 600 or something for now. And what I've taken out here is the ability to write the image. I just didn't want to write it to file because that takes a bit of time. But this will return the last image. So I'm just going to say image is going to be equal to this, and we'll say image 3 or something. And then we'll run that, give it just a second to do its thing. And then we should have an image that is smaller than the image that we had beforehand. And this should give us maybe just 1 more minute for Alan and friends to talk about why seam carving is, why we wanted to put it in the curriculum to begin with, because there's a lot of really cool stuff related to this and different curricula and Julia and all this kind of stuff. So
actually, before that, I just wanted to make a comment about Julia style. So you could have you could have used the same function name find seam for the 2 different versions of the function.
You're right.
Find seam and find seam add.
Right.
You could have just called both of them find seam.
Right, and then that would have, that actually probably would have been better.
You would create 2 different methods of the.
Right, we can do that right now if we want.
Yeah.
So all we have to do is change this to find seam.
It just enables you to think of fewer names. Finding names is always hard.
Right.
Yeah, it's just below.
Yeah, so if I just change that to find seam, it should work just fine. wherever
I
my
mean,
lesson clue
the
was.
two hardest problems in computer science, right? It's finding names of things, cache errors, and off by one errors.
Is that 2 or 3?
Well, that's the off by one error.
That's the joke. Oh, sorry, I'm being recorded.
So anyway, here we see seam carving completely implemented in what is roughly 25 minutes. I'm really hoping that this was, for me, I find a lot of intuition seeing people just write things out in code. And also you get to see a bunch of different coding styles. So I hope that was interesting for you guys. So yeah, Alan, do you want to talk about?
Real fast, since I have to switch to the local students, but yeah, why did we choose this? First of all, I just think this algorithm is cool, and that's sort of like that's sort of like the highest order bit. I mean, just like that you can do this so easily is really cool. Secondly, the idea of illustrating dynamic programming at an early stage of a computer science type class is another good thing to do. I mean, you have all these paths, and yet somehow if you work your way up by the magic of computer science, you find the best one. It's kind of a little miracle. Yep, just like that. And thirdly, and you'll see this in the reminiscing video if you happen to watch it, but I'll repeat it here in case you didn't see it, which is that this was a example of something that was from, there was a meeting at MIT figuring out which language to use. This was 5 years ago. Julia wasn't ready yet, but they asked about Julia at the time, and they said that Python was way too slow for doing this kind of computation, and they were wondering whether Julia would be able to do it so easily. And you know, that is one of the places where Julia shines, that it could just do this sort of thing real fast. You know, that is one of the places where Julia shines.
Ooh, there's some echo.
Yeah, let me. Yeah, okay. So yeah, so that's coming from the other Zoom meeting. Yeah, so I'll just finish with that since I have to run off.
Yeah. Okay. So I think this is actually a good place to stop then. We'll hop onto the other meeting with the MIT students. I guess if there's any last comments, go ahead and say them now. Otherwise, we'll go. All right. Great. So thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And hopefully we'll see you guys around for the next lecture. Should be next Tuesday. Should be a lot of fun. See you guys. Also, I don't have an end screen, so you're going to have to see this for 2 seconds.